Hello students, welcome to today's session of chemistry. As you all know, we have started studying 8th lesson of your syllabus, that is transition and inner transition elements. That means D block elements and F block elements. Of these two types, we just finished study of transition elements, that is D block. We also learned about extraction of metals in previous session. And now from today we are going to start studying about inner transition element, that is F block elements. As we all know, first and most important thing while studying any type of elements is its position in the periodic table. Because by knowing the position, we easily can predict the characteristics of those elements easily because the arrangement is very particular. So first we'll see the position of inner transition elements. As you all know, F block elements are there at the bottom of the periodic table. The elements are arranged in two horizontal rows containing 14 elements each. That means a block has total 28 elements. But the first series, the upper one called Lanthanoids, is there in the third group and sixth period. It is there LA 57 to 71. Why? The bottom series is there in the seventh period and third group. That is 89 to 103 AC it is written. So first series LA means lanthanum. And after lanthanum, the 14 elements are arranged in horizontal row. Lanthanum belongs to D block. After lanthanum, cerium is there, and from cerium to lutetium, these 14 elements are called lanthanoids. While the bottom series, that is, comes after actinum, hence these are actinoids, and they start from 90 thorium to 103 lawrencium. So, in all, there are 28 elements, 14 in each row. The upper series is known as lanthanoids and lower one is actinoids. We just have been introduced with these elements in the previous session. Now we will just learn about the properties of these inner transition elements, that is lanthanoids and actinoids. First, the definition. The elements whose n-2 f orbitals get filled up by electrons are called F block elements. The definition is common as that of P or D block element. That means when the last electron gets filled in particular shell or orbital, then that element belongs to that block only. Here, all the elements if we see and if we write the electronic configuration, we will see that last electron is in the f orbital. Hence, these are called as F block elements. Why it is written n-2? Because F is always pre-penultimate shell. It is not nth shell or n-1 shell, it is always n-2. As we have seen in case of transition elements, last but one shell is a D shell. Like that, last but second shell is F always. Now, next property is they are placed separately at the bottom of the periodic table and the arrangement is like this. We just have seen this arrangement. So, these are the F block elements arranged in two horizontal rows containing 14 elements each. Now, we will see the properties of F block elements one by one. Properties are similar to D block elements. These, as I told you, the F block elements are there in the D block itself. So position is same, that means properties are almost similar to transition elements. The electrons are added to F subshells of n-2 level. They are added to n-2 F level. That n-2 F level or these elements are placed between n-1D and n s block elements. Nth shell is final shell. That means, take example of a block elements, 4F series and 5F series. There are two series. 4F is lanthanides, 5F is actinoids. When 4F series starts filling up, at that time 6S is already fulfilled. 5D, 6S, 5D. 5D contains only 0 or 1 electron because it is in the first group itself. Third group is the first group of D block. So D block's first group, that means there are only 1 or 0 electron. Why 0 or 1? That depends on stability. So D block contains either 0 or 1 electron and F starts filling up. Which is F now? As 6S, 5D, 4F. So that will be nth, n minus 1, n minus 2. So 4F starts filling when 6S2, 5D 0 or 1, and then 4F 1 to 14 is Lanthanoid series. In the same way, actinoids will be in 5F series, that means 7S2, 6D 0 or 1, and 5F 1 to 14. That will be the general electronic configuration of lanthanides and actinides. Now, lanthanides begin with atomic number 57. Actually, 57 is lanthanum. From 58 cerium to 71 lutetium are the 14 lanthanides are there. These lanthanides in ancient times or historically they are termed as rare earth elements. They are found in earth crust and they found in very few percent, and their extraction is also difficult. Hence they are called rare earth element. But nowadays they are obtained fairly abundant in earth crust, but the name rare earth elements remains as it is. The name it is coined or it is said because of difficulty in extracting them economically in pure form from other lanthanoids having similar chemical properties. Understood? It is very difficult to extract. We have seen the extraction. Extraction is separation. Now, all the lanthanides belong to one square. If you see the position in the periodic table. So, they belong to third group and sixth period. Hence, all of them almost have similar properties. So, separate them from each other is very difficult and it is not economical as well. Hence, the name given is rare earth elements. Now, the properties. These metals are soft with moderate densities of about 7 gram per cubic centimeter. They have moderate density, not so hard, not so soft. They are soft enough. They have high melting points above 1000 degrees Celsius and high boiling points as well above 3000 degrees Celsius. Similar to groups 1 and 2, lanthanides are in the metallic state are very reactive and they resemble alkali and alkaline earth metals in their reactivities than transition metals. Now, similar to groups 1 and 2. In group 1 of the periodic table, which are the elements located? Do you remember? Those are alkali metals. And in second group, alkaline earth metals are there. And in the third group, inner transition elements are there. So, inner transition elements are near to S block elements. Transition element, that is D block elements, are located in 10 different groups. Hence, these elements, as they are in the first group of D block or they are near to alkali and alkaline earth metal, they resemble, they are similar in properties to that of alkali and alkaline earth metals than transition metals because of their position. So, These are very reactive metals as compared to that of transition metals. If we compare them with first and second group, that is metals, alkali metals, they also react with water to give metal hydroxide and hydrogen gas. This property is similar to that of alkali metals. The name alkali metals is given just because they give alkali with water. And similar to that, these elements also they form MOH thrice, that means alkali. So with water, these M for metal. These metal also form alkali. So lanthanum that reacts with water to give lanthanum hydroxide along with hydrogen. So liberation of hydrogen is the one of the characteristic property of metals, and formation of alkali is one of the property of alkali metals, that is strongest metals. So these elements, that is inner transition elements, are similar in properties to that of alkali and alkaline earth metals, and not that like that transition metals. Next property. The common oxidation state shown by lanthanoids is plus 3. Plus 3, that means 2 electrons from s orbital and 1 from d, or sometimes from f also, depending upon 0 or 1 electrons in d orbital. So plus 3 oxidation state is common for lanthanides, but sometimes they can show plus 2 oxidation state as well. That means last shell electrons only are donated in the s subshell. Hence, the common oxidation state shown by lanthanides is plus 3, but sometimes they also show plus 2 oxidation state. They all form stable oxide. That means when they are treated with oxygen, they form oxide of the formula M2O3. That means suppose we take cerium as an example, Ce2O3. M is for metal. So these elements, like alkali metals, they form M2O3 type of oxides. Out of these, UU plus 2, that means europium, and YB plus 2, that is ytterbium. These are the most stable dipositive metal ions. So, as I told you, plus 3 is common oxidation, but sometimes they show plus 2 also. Higher oxidation states are unusual. Lanthanides generally show plus 3 oxidation state. Only cerium is the exception, which shows plus 4 oxidation state. Now, next property. The energy required to break up the metal lattice is called heat of atomization. Suppose we have taken a crystal lattice of any of the metal of inner transition elements, and if you want to break up into atoms, then that energy required to break up the metal lattice is called heat of atomization. And lanthanides have lower heat of atomization than transition elements, because with d electrons, transition metals are much harder. As lanthanides resemble that of alkali metals, these are soft, hence low heat of atomization. They require very less heat, but d block elements are much harder, hence they require high heat of atomization. Next property. The ionic radii decreases from 117 picometer that of lanthanum to 100 picometer of lutetium. So from first member to last member of lanthanides, if we see the atomic and ionic radii particularly, that decreases from 117 to 100 picometer. That means we observe decrease in the atomic radii or ionic radii as well. This is because if we consider that of lanthanides, then 4f orbitals are located very much inside as compared to 4s and 4p. So, When the electrons are added to 4f orbitals, these electrons, they do not show any of the shielding effect because it is located very much inside, and hence the nucleus or the effective nuclear charge gets increased because of the addition of electron every time in the nucleus, in the outermost shell, and proton in the nucleus. Thus, effective nuclear charge increases as the power of the nucleus increases, but there is no effect, shielding effect, or any other effect on the outermost electrons. And as a result, there we observe a decrease in the ionic radii from lanthanum to lutetium. As the ions of F block elements are larger in size, so if you see the 100 picometer sizes of lutetium, 117 picometer that of lanthanum, this is relatively larger size. And because of this larger size, these ions have a capacity to attach more number of other atoms to form a complex. These inner transition elements have a tendency to form metal complexes. That means they attach more than one type of metal atom and more in number as well. That means the coordination number varies from 6 up to 12 in some cases. Coordination number is number of other atoms attached to central metal atom. As the central metal atom in this case is inner transition element and it has a tendency to form metal complexes, the coordination number is also large, shown by these elements. For example, hydrated lanthanum ion. Lanthanum ion can attach 9 water molecules. That means it can form nonahydrate. So, because of the bigger size, this is possible. All the lanthanoids, they form hydroxides. So, this property is similar to that of alkali and alkaline earth metals to form alkalis, or we say hydroxides, with the formula LNOH thrice because plus 3 is the common oxidation state shown by lanthanum. That means Ln plus 3 OH minus 1. So, Ln represents lanthanoids. These hydroxides, that means LNOH thrice, they form alkali, we said. As we say this is alkali, that means they are basic. So, all these hydroxides are basic and ionic. Ionic LNOH thrice, that means Ln plus 3 OH minus 1. Together they form, when they form compound, they form LNOH3. So, all these hydrides are ionic and basic. And as we have seen that ionic radii decreases from lanthanum to lutetium, that is 117 picometer to 100 picometer. The basicity of hydroxides also decreases in that order. That is from lanthanum to lutetium, basicity decreases. That means lanthanum trihydroxide or LaOH thrice is the strongest base, while LuOH thrice, lutetium trihydroxide, is the weakest base. Lanthanides react with nitrogen to form nitrides like LNN, while they also react with halogens to form LNX3. That means halides. X means halogen. So, lanthanum nitrides and lanthanum halides are easily formed by lanthanoids as they are metals. They easily react with non-metals. And while doing so, lanthanides lose their outermost 3 electrons to form a stable compound in plus 3 oxidation state. As I told you, plus 3 oxidation state is common. So, LNX3 means Ln plus 3. They lose their 3 electrons which are in the outermost shell, and X minus 1, that means they form stable compounds in plus 3 oxidation state. When lanthanides are heated at elevated temperature, that is about 2800 Kelvin, such a high temperature, with carbon, they form carbides of the formula LnC2. So, lanthanum carbide. They form easily because again carbon is non-metal. In +3 oxidation state, many of the lanthanides are colored. So, in their ionic state, they are colored like green, pink, yellow, various type of colors they show. So, these are the properties of Ebb block elements. We'll just collect them. So, properties of lanthanides are like this. These are the soft metals with silvery white color and moderate densities, that is 7 gram per cubic centimeter. Color and brightness of these metals that gets reduced on exposure to air. Why again? This is because of the reaction with oxygen in the air. They get converted into their oxides and hence their color and brightness reduces, a kind of corrosion, we say. These are metals and they are good conductors of heat and electricity. Except promethium, all the lanthanides are non-radioactive in nature. Only promethium is radioactive, in lanthanides particularly. The atomic and ionic radii, as we say, that decreases from first element to last element, that is La to Lu, and that is called as lanthanoid contraction. It is very rare thing. As you see, all the elements belong to one square, that is one group only. All are third group elements and sixth period, but still there is reduction in the ionic size. We have seen the reasons. Hence, this reduction in size is called as lanthanoid contraction. A note is asked many a times in the exam. We are going to see in detail about lanthanoid contraction later. Now, next property. Binding to water is common. We have seen the example of lanthanum monohydrate. So, water molecules are easily get attached to the central metal atom of inner transition series. So, binding of water is common. Water, because water is often found in products. When they are separated in aqueous solution, we get water. So, that means they, while forming crystal lattice, they get attached to water molecules. Coordination numbers are usually greater than 6. So from 8, 9 up to 12 also we get coordination number. That means these metal ions are larger in size. So they get attached to such a large number of other metal atoms. The lanthanoids are strongly paramagnetic. Now you know very well what is paramagnetism. We learned it in while studying transition elements. As these elements, they are paramagnetic. What will be the reason? As again, that comes in the electronic configuration. Reason is that F orbital has a capacity to accommodate 14 electrons because F has 7 orbitals, 7 different orientations. And as per Hund's rule, when the electrons are added, they first occupy all the orbitals singly and then pairing starts. And that means there are so many unpaired electrons in the outermost shell. And this is the reason why these elements are strongly paramagnetic and sometimes ferromagnetic as well. So gadolinium, it becomes ferromagnetic below 16 degrees Celsius. So 16 degrees Celsius, below that it becomes ferromagnetic. That means the property of magnetism increases so much that it can permanently become a magnet. Again, heavier elements of lanthanides like terbium, dysprosium, holmium, erbium, thulium, ytterbium, They also can become ferromagnetic at much lower temperature. That means generally if you observe the elements which are at the center of the lanthanoids, they have larger number of unpaired electrons and hence they can easily become ferromagnetic. They are strongly paramagnetic, so can easily become ferromagnetic at lower temperatures. And the last properties, magnetic and optical properties are largely independent of environment. Magnetic properties, just we have seen this paramagnetism and ferromagnetism. And optical properties, as we learn in transition elements, these are largely independent of environment. They doesn't depend on the environmental factors. So these are the properties of F block elements. Now, the time for assignment. Write any 6 important properties of F block elements and lanthanides. 6 each. Understood? So, thank you.